Allow me to start by telling you a little more about the factory itself. It stands on three pillars. Naturally, we need to produce these isotopes, curium, berkelium, and californium. Obviously, we need to create a more powerful accelerator. And of course, we need to make more sophisticated equipment which would allow us to measure a multitude of parameters at once. So we hope to increase isotope production up to 10 times by improving the operation of the high-flux reactor at Oak Ridge. Going forward, we will refer to this in factors, this specifically being a factor of 10. Here in Dubna, we will create a new heavy-ion accelerator, which will have a beam intensity 10 to 20 times greater than the current accelerator. We will also create a more sophisticated design of our equipment, especially our separators, in order to gain time by a factor of 3 to 5, which will enable us to measure many parameters simultaneously, instead of measuring them sequentially. As for the reactor, we have already talked about this in a previous lecture. Considerable progress was made when the starting material was changed, and instead of plutonium, we now start with curium, resulting in the gain of a factor of 6.5. I believe this can be improved up to a factor of 10. But there is also another option that we have used in the past, and we are familiar with the technology involved in isolating californium fractions from old sources of californium, so that the heaviest isotope, californium-251, can be used as target material. For this, we require a separator which can separate these isotopes of californium. The price of such a separator is approximately $10 million. So we took this up with our American partners, and they added the construction of this separator into their plan for 2020. Unfortunately, life tends to move much faster than our plans do. In the American plan of the Department of Energy, it states that it is necessary to produce targets for the super heavy element factory in Dubna, and that it is also necessary to construct an isotope separator in Oak Ridge for these works. This is the team that works for us in Oak Ridge, which roughly consists of around 50 staff members from different departments. As far as the accelerator is concerned, we need to increase the beam doses, and this requires an increase in the intensity of the beam as well as in the beam time. Today we have the opportunity to collect about 4.5 times 10 to the power of 19 calcium-48 ions in our accelerator per year. When we build the new accelerator, we will increase the beam intensity to around 10 to 20 microamperes. And the Xi factory will operate all year round. Due to this duration of work, and by increasing the intensity, we will increase the production rate by 1.3 times 10 to the power of 21. That is, we should gain a factor of around 30. The accelerator is unique in that it was specifically created for this task. Our accelerator engineers, Gulbenkian and his group, calculated the energy and amount of particles that are needed, as well as the maximum intensity that it can produce. It became clear that the accelerator will double as a cyclotron, as it is equipped with high-voltage sources. This is a struggle against the space charge, because a large intensity moves in the vertical channel of the beam to the center, and then it starts to accelerate. These are the intensities of the beams. With the increased intensities, we can obtain both titanium and zinc, even up to krypton. In principle, it is possible to obtain uranium, but the priority is using calcium and zinc in order to reach our goal of 100 factors. Unfortunately, we do not have the time to discuss all of the equipment and procedures involved. Please note the different types of special separators that will be used for these experiments, and the principle of the experiment will be slightly different. At present, the process is as follows. Here is a beam, and there is an actinide target at the target station. The separator almost completely removes calcium-48 and collects other reaction products. The calculation is based on the fact that it would be necessary to carefully collect superheavy elements and move them into the detector system. All further analyses will take place within the detectors. Therefore, the selection of reaction products that interests us accumulates in the detectors. This means that the selection takes place twice, once here and the second time in the detector. However, we want to do it a little differently by removing the detector and replacing it with an interface. The new addition is the so-called gas collection chamber, or gas catcher, as it is called in English, which forms a high-quality beam from this beam of recoil nuclei that moves through the gas catcher. It forms relatively quickly, in 5 milliseconds. All of the nuclei we are talking about have a lifetime of more than 5 milliseconds, or at least most of them do. Therefore, we can pull them out from here in the form of a beam of super heavy elements, pass the beam through the analyzer, determine the atomic number and mass of the nuclei, drive them further, and if necessary, either accelerate or slow them down, depending on what is needed, and then collect them in the detectors. At the end of the process is a collection of detectors that are spread out. We will be online for each event to identify its charge mass and observe any decays. This system will result in a tremendous gain in time, whereby we gain another 5 to 10 factors. This brings us to 100 factors, and it is composed of the following effects: registration, acceleration, targets, and so on. This is the progress that will allow us to carry out experiments at a whole new level. It is necessary to approach the superheavy nuclei as we would ordinary nuclei, and to evaluate them in the same way as all other nuclei. It is possible that only 2 or 3 experiments will be carried out at this factory per year, but each experiment will have thousands of events, and the amount of data that will be collected from these thousands of events will most likely reveal much more than what I have told you during these 5 lectures. A lot of people from different laboratories all over the world are interested in this factory. I would like to mention all of the collaborators working together to turn this into a reality, starting with Oak Ridge, which is producing the targets, Livermore, which cooperates with us. This is the Argonne National Laboratory, where the gas catcher is being made. This is Darmstadt. This is the University of Texas. This is the French National Laboratory. This is Dimitrovgrad in Russia, where there is also a powerful reactor, and this is Vanderbilt University in Nashville. Thank you for your attention.